Okay, so the next speaker is Tom Hutchcroft from Caltech, and he's going to talk about uniqueness and non-uniqueness for percolation on groups.
Thank you. Thank you all for being here. Thanks to the organizers for inviting me. This is going to be a very introductory talk, mostly. I'm going to talk through a lot of old things that were done 20 years ago, and I'll emphasize things that are still open, particularly things that have a kind of a groupy flavor that maybe people in this audience will like to attack themselves. And if time permitting, I may mention some more recent things at the end, but the focus will be more on the introduction. Okay, so let me start by just defining percolation. So we'll start with a graph, which will be connected locally finite. So locally finite just means that all the vertex degrees are finite. Yeah, connected and locally finite. These two assumptions I'm just always going to have, so I'm not going to keep mentioning them just to keep things from being non-degenerate. Okay, and usually I'm going to assume that G is like a Cayley graph or more generally a transitive graph, but for now, let's stick to just this very high level of generality. Okay, and I'm going to be looking at what's called Bernoulli P bond percolation. And what that means is that we keep or delete each edge independently where we keep with probability P. Okay. Now, of course, one can consider much more general classes of random subgraph models, and many of the things I'll say are actually sort of equally applicable at a much higher level of generality, but most of the most interesting stuff already appears in this very simple model, so let's keep it at this in this specific case. Okay, so a few terminological things. So the edges that we keep are called open. The edges that we delete are called closed. And the connected components are called clusters. Okay. So generally speaking, the kind of thing you're interested in, you start with your graph, you take this random subgraph in a way that depends on this parameter, and you're interested in, what do these clusters look like? What is their geometry like? How does this change as the parameter P is varied? So the first sort of important definition is that we define the critical probability, PC, to be the infemal value of P, and I should say, I'll write P subscript P for the law of this random graph. So PC be the infemal value of P where infinite clusters exist with positive probability. Okay, and in fact, it has to be equal to 1 because by Kolmogorov 0-1 law, this is a tail event for a bunch of independent random variables, so it's a 0-1 event. Yeah. Oh, it means a cluster that is infinite. Yeah, yeah. Otherwise, if P is 0 and G is, then every vertex will be its own cluster. Okay, cool. Sorry, I feel like I'm going to fall over at any moment with the water on the stage if I'm walking like this. So, okay, so the first basic thing to notice about this is that PC is always positive, provided the graph is bounded degree, which for a Cayley graph, all the degrees are the same. So in particular, PC is always bounded below by this, where this is the max degree. Okay, so this is just a simple counting argument. Suppose I look at the probability at P that let's fix a vertex. And I say, what's the probability that this vertex belongs to an open path of length at least n? Well, by Markov's inequality, it's bounded by the expected number of open paths of length. Well, of course, if it's in an open path of length at least n, it's in an open path of length equal to n. Right? But if I take a particular path, right, the probability all the edges in that path of length n are open is p to the n, right? They're independent. And how many possible paths are there? Well, you can imagine this is just an upper bound, right? But, you know, the first edge of the path, you get degree choices. Each subsequent edge, you get degree -1 because you want it to be a simple path. Right? So you see that if p is strictly less than this, then this goes to 0. Right, so that means the probability that the origin belongs to a path of length n goes to 0 as n goes to infinity. Of course, if the origin had a positive probability to belong to an infinite cluster, you know, there's this Koenig's lemma or something that if you have an infinite graph, it contains an infinite path for every vertex if it's locally finite. So, you know, this implies that when p is less than 1 over max degree -1, you don't have an infinite. It's very simple, just elementary counting. Now, the question of whether PC is smaller than 1, so in other words, whether you really have this, what we think of as a phase transition from a phase with no infinite clusters to a phase where infinite clusters exist. This question is much more subtle. The most classical case, I think I misspelled this name, but is due to the Rudolf Peil. So he was actually studying the ESI model. The argument works for percolation. It's actually quite a lot simpler for percolation. So he proved that it follows from his argument that if you look at the square grid, PC is less than 1. In fact, it gives that it's smaller than 2/3. Okay, and the argument is basically you do the same thing as this, except you work in the planar dual and you count like curves that could block you from being an infinite cluster. So if you imagine, let's say we have the square grid, we have the origin here. Now, if the origin is in a finite cluster, you can look at all the dual edges. I'm missing another color, but if you look at the dual edges that surround this finite cluster, these edges will form, well, the outer boundary of them will form a cycle in the planar dual. Okay, but you can do something similar to what you did here, where you can count basically how many possible cycles there are. Now, and for each one, the whole thing has to be closed, right? So you get basically, in order to have a particular thing, you get 1 minus p to the n. This is the probability that all of this dual cycle is closed, where n is the length of the cycle. And then if it has length n, it has to, you know, the counting problem is a little bit more subtle because these paths don't have to start at the origin, right? But they all have to cross the positive real axis somewhere. If it has length n, it has to cross within the first n things. So you get something like this on the bound of the expected number of these closed dual paths that wrap around the origin, right? Now, again, if p is bigger than 2/3, you'll see that the expected number of these closed dual circuits that go around the origin is finite. And from there, it's not too hard to say that there's a positive probability that there are none of them. So one thing that you can easily deduce from this Peil's argument is that if you take any hypercubic grid of dimension at least 2, then you're also going to get PC is smaller than 1. And this is just for the trivial reason that PC of the subgraph is bigger than the PC of the big graph. Now, in fact, we now know that this thing that you have a phase transition holds extremely generally. So this is a theorem from, I don't know, 4 years ago, 5 years ago, Dumno-Kapan, Goswami, Ralphie, Severo, and Yudin. And what they showed is that if G is transitive, and what this means is that, for all vertices U and V, there exists an automorphism with mapping U to V. So for transitive graphs, PC is less than 1, if and only if G is not one-dimensional. Okay, so there are a few equivalent ways of formulating this. One is that G is not quasi-isometric to the integers, or equivalently, the volume of balls grow much faster than linear. Okay, in fact, there's all this structure theory of groups of polynomial growth that says if the volume of a ball grows faster than linear, it must actually grow at least quadratically. So equivalently, you could say PC is strictly less than 1, if and only if the growth is at least quadratic. Okay, so this theorem is really just the end of like a long story with work on various cases of this. So in fact, at the time that they proved the full conjecture, it was only still open for groups of intermediate growth. So when you have polynomial growth, in fact, you always contain like a quasi-isometric copy of Z squared, basically, under this condition. So you can just use these classical things together with these embedding things, you get the polynomial growth case. And in the exponential growth case, there are various quite simple arguments for why PC is strictly less than 1. In fact, you can say that PC is less than or equal to 1 over the exponential growth rate of the group. Very, very explicit. Okay. What's that? Oh, yeah, it's, sorry, I didn't want to write them all out, but it's Dumno-Kapan, Goswami, Ralphie, Severo, and Yudin. And Yudin is over there. Good. Okay, so basically what they're saying is, one-dimensional things are just not very interesting from the perspective of percolation, right? If you're one-dimensional, like if you have Z, as soon as P is less than 1, you're always going to delete some edges, and every time you delete some edges, you're going to cut things up into finite pieces. Just, nothing interesting happens. But as soon as you're not one-dimensional anymore, then you actually do have this phase transition where you get these two different phases. First, you have no infinite clusters, then you have infinite clusters. PC is the dividing line between these two phases. Yeah. Yes. So PC being smaller than 1 is a quasi-isometry invariant, but the value of PC is highly sensitive. And generally, this is something where if you, in percolation more generally, things about percolation very close to 0 and 1, in like a neighborhood of 0 and 1 will be quasi-isometry invariant, but the neighborhood will change. So if you want to study things like where you're not looking at small neighborhoods around 0 and 1, it's not going to be quasi-isometry invariant. On the other hand, you kind of expect the behavior in a group to actually be to end up being quasi-isometry invariant, but not because it's quasi-isometry invariant for all graphs, just because it will probably be equivalent to something else, which is quasi-isometry invariant. That will hopefully become clear in a second. The one thing I should mention for this example, so the arguments we just saw said that if you look at PC of the square grid, it's between 1/3 and 1/2. So this is very easy. In fact, for this specific graph, it's a theorem of Keston from the 80s that PC of the square grid is exactly equal to 1/2. Okay. Now, I just want to mention this quickly. It's not so relevant the rest of my talk. This is ultimately a consequence of the fact that the square grid is its own planar dual. One thing I want to stress, though, is that being able to compute the critical probability is highly atypical. You know, it's really, don't get the wrong picture from this. For most graphs, you're not going to be able to know exactly what the critical probability is. For example, for the cubic grid, it's probably some transcendental number that doesn't really have any nicer description than this implicit one. So, you know, generally speaking, if you want to understand stuff about critical percolation, things like that, you have to work with the implicit definition, which prevents you from doing various kind of like more direct counting type arguments. Okay. So when P is larger than PC, by definition, you have infinite clusters, right? So perhaps the most basic question you can then ask is that, you know, how many infinite clusters do I have, right? So the first basic theorem, so this is due to Newman and Shulman, it's from the early 80s, is that if G is transitive, then for each P, there exists K, which is either 0, 1, or infinity, such that the number of infinite clusters is equal to K almost surely. Okay. And I'll write big N for the number of infinite clusters because I'm going to be writing a lot. Okay, so in other words, the number of infinite clusters is not random, right? It's almost surely equal to some constant, and that constant is either 0, 1, or infinity. So it can't be that you almost surely have, you know, 5 clusters or whatever. Okay, the proof of this is very simple. Basically, the idea is that, well, first of all, the fact that you have a non-random number of infinite clusters is just the ergodic theorem. So, you know, if you've ever learned any ergodic theory, this is a very straightforward argument. The fact that it can't be a finite number other than 0 and 1, basically the idea is that if it was, let's say it was 5, right? Now, if it's 5, it has to always be 5 with almost surely, right? But if that's the case, if I take a large enough ball, there's a positive probability that it intersects all 5 of my infinite clusters. Okay, in particular, there's a positive probability that the union of the actual random graph I have with all the edges in this ball has a unique infinite cluster, right? Now that event only depends on what's outside the ball, right? So it's independent of what the edges inside the ball are actually doing. So as a consequence, you have a positive probability that the intersection of that event with the event that all the edges inside the ball are open, well, it's, you know, it's a product of 2 positive things, so it's positive. Okay, so therefore, you've said that in fact there's a positive probability that there's 1 infinite cluster, right? But you assumed for contradiction that you had 5 infinite clusters almost surely, right? So you get a contradiction. That's basically the whole argument, you know, in the 15-second version. Okay, so. So, you know, once you have that, there's then this question, well, okay, I know that it's when I'm above PC, I either have a unique infinite cluster or infinitely many, but which is it? And I should say this was an open problem for a long time. You know, it was solved in the 80s, but, you know, this problem was posed in the 50s, so it was, you know, 30-year problem. And so this, in the case of the hypercubic lattice, it was solved by Eisenman, Keston, and Newman in like 86 or something. And then there was a simpler and more general proof due to Burton and Keene like 2 years later, which is the one people usually learn now. Although the original proof of Eisenman, Kester, Newman has much stronger quantitative outputs. And this is that for percolation. What? Oh yeah, it's Eisenman, Kester, Newman, and Burton, Keene. Yeah, sorry, there's going to be a lot of like names because of, sorry, I don't want to bore you by writing down names all the time. So if you look at the hypercubic lattice ZD, there's at most one infinite cluster, almost surely. Okay, so I'll give you, again, the sort of 2-minute version of the Burton-Keene proof of this. So of course, I'm going to put a lot under the rug, but this is really a classic, very elegant proof, or at least it's very elegant, except for the bits I'm not going to explain, which are less elegant. Okay, so here's the idea. Yeah, so for each P, in other words, for any P, this N is equal to 1, 0 or 1 almost surely. This K is always 0 or 1. Okay, so here's the Burton-Keene. Again, the extremely quick version of the Burton-Keene proof. Okay, so here's the first part where I'm just going to cheat completely and not really explain it. So if you, we know that if you don't have one cluster, you have infinitely many. So in particular, you have at least 3. Okay, so they say, let's say you have at least 3 infinite clusters. Okay, so doing something similar to what I did before, where I said, you can kind of condition on what happens outside the ball and then put any forced configuration you want inside the ball, you can like arrange for this picture to happen. So what this means, this is a trifurcation point. Okay, so what this means is that this is a vertex which belongs to an infinite cluster. And if you delete that vertex from its cluster, you separate that cluster into at least 3 connected components. Okay? So what they first show is that if you have infinitely many infinite clusters almost surely, then you have a positive probability that trifurcation points exist. Okay, and this is kind of the inelegant part of the argument where you have to figure out how to do this surgery to force them to exist. Okay, but the model's translation invariant, right? So that means that the probability, and let's call this set of trifurcation points T. Right, so the probability that X is a trifurcation point is some constant that doesn't depend on X, right? It's positive. Every point has the same probability. So then what they do is they say, suppose you take a finite set of vertices lambda, right? Now, trivially, if you look at the expected size of the set of trifurcations that are inside lambda, well, this is just equal to C times the size of lambda. This is just by linearity of the expectation. Okay. Now, on the other hand, and this is again where I'm just going to cheat and just tell you something. It turns out that if you look at this set of trifurcation points inside lambda, let me get one here. Okay. It's a combinatorial fact. It's basically a sort of Euler's formula thing at the end of the day. It's quite simple. But however many trifurcation points you have inside lambda, and of course, they might not all belong to the same cluster. It's not so good. However many trifurcation points you have in lambda, you can find a disjoint set of paths from the set lambda to infinity that has size at least that number of trifurcations, right? So in particular, if you have this disjoint set of infinite parts that has size at least this, then the boundary of lambda, the edge boundary, has to have at least that size as well, just because, you know, these parts all have to start at distinct edges. So, you know, some elementary combinatorics shows you that the edge boundary of lambda is at least the number of trifurcations inside lambda. Okay, so you just put these things together, and you get that the edge boundary of lambda is at least c times the size of lambda. And this holds for any set lambda, so it means with a uniform c, so you deduce that a hypercubic grid is non-amenable, which is false. Right, so as a reminder, you know, yeah. Yeah, well, I'll get to that. Yeah. Okay, so really, you know, they phrase their argument as saying that for the hypercubic grid, that you have at most one infinite cluster. But it's really any amenable transitive graph. Okay. Well, I don't know. Do you have a word that applies to the square grid, the cubic grid, and the hypercubic grid? That's not hypercubic. No, I mean D at least. At least one. I mean, it's also true in one dimension. This or zero even. It's just not very interesting in one dimension or zero dimensions. Okay. Good. So, and just to remind you, non-amenability of a graph precisely means that an inequality of this form holds for all sets, right? It means that for any set, the boundary of the set is at least some universal constant, not depending on the set, times the volume of the set. Okay, so ZD, this inequality is not true on ZD because if you take a big box, right, side length n, its volume scales like n to the d, but its boundary scales like n to the d minus 1, right? So if you plug that choice of lambda in here, you'd see that this inequality can't be true for all lambda. Yeah.
Lambda is not amenable. Lambda is not amenable.
Lambda is a finite set. Sorry, lambda was just a
cluster lambda.
Lambda is just a set of vertices. It's deterministic. Think of it as a box.
I thought it was a cluster.
Yeah, sorry. Yeah. I think if it was random, you couldn't use the linearity.
But this argument that works for G equals 2 also, this
Yeah, it's I mean, you know, it's a contradiction. Ultimately, you get a contradiction, right? I mean, this whole picture never actually occurs. But okay. So that's the Buttonkian proof. Okay. And the one of the big conjectures in this area, which is due to Benjamini and Schramm, '98, is that the converse is also true. So in other words, if you have a non-amenable transitive graph, there should exist a value of P where there are infinitely many infinite clusters. Okay. I should say this paper of Benjamini Schramm, it's called Percolation Beyond ZD, Many Questions and a Few Answers. It contains a lot of conjectures, several of which are still open. This theorem of Dimnu-Kampan, Goswami, Ralphie, Savara, and Yadin was the solution to one of the other conjectures in that paper. Good. So let me tell you a little bit about what's known about this problem. So the first case people studied a lot was when you, instead of just assuming that your graph is non-amenable, you assume that it's like very non-amenable in some sense. Okay, so And basically, if you assume something like this, so for example, one way of defining non-amenability by Keston's theorem is that if you look at the return probabilities of the random walk on your graph, the limit, basically the exponential decay rate, you have to do even times to make it work in general. This is what's called the spectral radius of the graph. Keston proved that G is non-amenable and only if rho is less than 1. And one of the things that's known, and this is due to Pak and Nagnabeda, I guess I should have written there. Is that if you have the stronger thing that the spectral, this is called the spectral radius, if it's less than 1/2 rather than just smaller than 1, then the conjecture is true. Okay, and basically, and there are a lot of variations on these other similar things where you assume some strong quantitative form of non-amenability. I won't go through them all. But the idea behind all of these things is basically you can just like explicitly do counting arguments to just carve out this regime where there are infinitely many infinite clusters by like counting parts and things like that. So direct combinatorial arguments that will, give you some bound on when you, some upper bound on PC, some lower bound on when you have a unique infinite cluster, and you just try to manually separate these by getting the parameters out nicely. The one nice consequence of this, though, it's not completely obvious, but it turns out that if you have a non-amenable group, it always has at least one generating set for which this holds. In fact, you can find generating sets where the spectral radius is arbitrarily small. So as a consequence of this, it means that every non-amenable group has at least one Cayley graph for which the conjecture is true. But again, these things are really not quasi-isometry invariant. I mean, they should, for groups, they should be equivalent to non-amenability, which certainly is quasi-isometry invariant, but you can't like directly argue.
Take note of that.
Oh, yeah.
So I mean, you said convert, but
Yeah, okay, let me say it exactly. So it's if G is transitive, then there exists P with infinitely many clusters, infinite clusters, if and only if, yeah. So, I mean, the conjecture is really just that if it's not amenable, then the other direction is the button. It should be infinite.
has anyone ever given interesting proof of non-amenability using?
I don't think so. It's like proving this is so much harder than proving non-amenability. Okay. So this is one thing, you put strong quantitative things in place, you can argue by counting arguments. There's a few other cases that are understood that are not like this. So one is that planar graphs, there we understand everything very well. So this was done first by Steve Lally and then completely by Benjamin and Schramm a few years later. This is all in like the late 90s, early 2000s. I won't say what this means, but any group of cost larger than 1, this is a result of Russ lines that you always have PC less, that you always have this phase where there are infinitely many infinite clusters. And more recently, I showed that it's true if you have a non-unimodular transitive subgroup. Of automorphisms. So again, I won't really go into this, but this, for example, if you have a product of a 3 regular tree with any other graph, then you're in this case. And I also showed that it's true for any gram of hyperbolic transitive graph. So this is basically the state of this conjecture now. The trouble is, it's hard to know what the next case is to attack, really. You know, I think like property T is quite natural, just because, you know, it's an assumption that's stronger than non-amenability, right, that people like to work with. But nobody's had any idea about how it's actually relevant to the problem. So yeah, anyway, it's not really clear what to try next. One thing I should mention, if there are people in the audience who are experts on things that are a bit weaker than hyperbolicity, that's a pretty natural thing to try. I don't know so much about those weakenings of hyperbolicity myself, but I'd be happy to talk about this if anyone's interested in that kind of stuff. Okay. So rather than talk more about this, I want to just keep surveying everything that's ever been done. So an important thing to understand what's going on with this conjecture as well is there's a theorem of Hagström, Paris, and Schonman. Which says that if you have a unique infinite cluster, again, this is for transitive graphs. Everything I say will be about transitive graphs from now on. If you have a unique infinite cluster at some p, then you have a unique infinite cluster at every larger value of p. Okay, and this is not at all obvious because having a unique infinite cluster, it's not deterministically a monotone function of which edges are open, right? You could imagine that you have a unique infinite cluster and then some edges open somewhere else and create a new one that's somewhere else. So it's not deterministically monotone, but it is, it turns out, monotone in the configurations that actually arise in percolation. Okay, so what this means is that basically you get this simple phase diagram where you get this second potentially different special value PU, where you see this picture. So first from 0 to PC, you have no infinite clusters. Between PC and PU, you have infinitely many infinite clusters. And then from PU to 1, you have a unique infinite cluster. So PU is just defined to be the infemal value where you have a unique infinite cluster. Okay, so of course, this theorem does not tell you that these intervals are non-empty, right? It just tells you that you have at most these 3 phases in this order. Okay, and of course, it also doesn't tell you anything about what happens at the boundary points, PC and PU. This is an extremely delicate problem that I'll hopefully tell you a bit about in a minute. Good. So, you know, actually the way this conjecture is normally talked about, this Benjamini-Schramm conjecture, is the PC versus PU problem. So the conjecture is equivalent to saying that PC is equal to PU if and only if the graph is amenable for transitive graphs. Okay. Okay, so one nice conjecture to mention here. So this is another conjecture from the Benjamini-Schramm paper, the one with loads of conjectures. And this is a conjecture I think is particularly nice for group theorists, is that you have this non-uniqueness phase, sorry, you have the uniqueness phase is non-empty if and only if G is one-ended. Okay, and the Babson and Benjamini showed that it's true for finitely presented groups. And basically, finitely presented groups are kind of the maximum level of generality at which you can run something like this piles argument that I talked about right at the beginning of the talk, where you like enumerate over sort of blocking surfaces and things like that, and do counting arguments. Okay, so it's known in the finitely presented case, but it's open in general. And you know, I think most of the conjectures in their paper I kind of believe are true. This one I believe less. I don't know. I mean, it could go either way. I think if you're a group theorist and you like constructing weird groups, this is a nice problem to maybe try to construct a counterexample. You know, you can imagine you have something that's one-ended, but like in a very quantitatively poor way, like where you have like large annuli where it looks like you're branching, and then, oh, I found that they actually connect back up again, like extremely far away or something like that. You know, if you can construct weird groups a bit like that, maybe you can find a counterexample. Okay. So in the final part of the talk, let me tell you a bit about what's known about these very subtle questions of what happens when you're exactly at one of these two boundary points. Yeah.
Directions.
Oh, yeah. So the one direction is trivial. If you're not one-ended, then PU is equal to 1. Yeah, that one's easy. But yeah, it's the other direction. Okay. Yeah. Okay. So what about let's start by talking about PC, and this is one that has received a lot of attention for many years. So the conjecture here, again, due to Benjamin and Schramm, although, you know, specific cases of this about hypercubic lattices and so on are much older, is that if PC is less than 1, so in other words, if you're not one-dimensional, then there are no infinite clusters at PC. Okay, and so again, this is like a really famous problem, not so much the very general form, but for the very concrete form of the cubic grid, for example. And basically, what's known here. Okay, so the first thing, of course, you try is a tree. This is easy. The percolation on trees are like branching processes. This is something you can teach in your, you know, undergraduate courses on probability. The case of the square grid was solved by Keston in the 80s. And, you know, 2 dimensions is extremely special. There are loads of, you know, all the topology of plane curves, things like that, the planar duality. There are lots of reasons why this case is particularly nice. Although we do now have much more robust proofs of this that will apply to like things that are just quasi-isometric to the plane without actually being planar, where you lose a lot of these tools. Okay. ZD with D large, and large here means much larger than 6. Of course, being much larger than 6 is the same as being much larger than 1, but this is the right way to think about it. So this was done by Hara and Slade in the 90s. And the reason why it's good to think of dimension being much larger than 6 is that basically the behavior of critical percolation is supposed to change in 6 dimensions so that it kind of becomes simpler. And really, their proof doesn't just prove that there are no infinite clusters at PC, it proves this kind of simple critical behavior, or what's called mean field critical behavior. So their proof techniques kind of definitely can't work below 6 dimensions. Although as it happens, they need the dimension to be like a large parameter for their proofs to work. The current world record is D at least 11. This was done by Fitzner and van der Hofstad fairly recently by sort of computer-assisted optimizations of the Hara and Slade method. Okay. And these sort of intermediate dimensional cases of 3, 4, 5, and 6, we really have no idea how to approach them. This seems like a very hard problem. On the other hand, this problem is understood much better for like big groups. You can kind of see even in this Euclidean case, things are kind of, okay, 2 dimensions is special. That's an outlier to this general rule. But things become simpler as we move to higher dimensions. So, most sort of big groups, which are like sort of infinite dimensional in some sense, easier. And so the Benjamini, Lyons, Perez, and Schramm in like 1999 or something proves that the conjecture is true for all non-amenable groups. So if you have a non-amenable group, there are no infinite clusters at PC. Okay. And in my PhD thesis, I showed that it's also true for groups of exponential volume growth, which might be amenable. Okay. Then after that, I had to work with Jonathan Herman. Where we showed the conjecture for some groups of intermediate growth. The exact condition is that if you look at the return probabilities on the group, they decay at least like a power, e to the power of n bigger than a half. So annoyingly, this does not include like the most famous examples of groups of intermediate growth, like the Grigorchuk group, but there are examples that it's a non-vacuous path. Okay. I should say another thing is that, if there are people here who like working on groups of intermediate growth, getting this exponent down is a very nice problem. I'd be happy to talk to you about. Okay. But anyway, that's kind of the state of this conjecture. So it gets easier as the group gets bigger, basically. Okay. Now, so there's one thing I haven't told you about yet, and hopefully I have time to do that. I guess not. Sorry about that. Okay, well, there's the last question, of course, is what happens at PU? This turns out to be a very subtle problem. There's very little work on it. The list of examples that are understood is quite small. And basically, in every example where it's known, it's equivalent to whether the first L2 Betti number of the group is positive. So in the examples where sometimes you get a 1 infinite cluster at PU. In all the examples that are known, you have positive first L2 Betti number. In some examples, you have infinitely many clusters at PU. In all the examples that are known, you have 0 first L2 Betti number. But there's so few examples that it might just be a coincidence. We don't actually know that it's invariant under changing the generating set, all that kind of thing. So this is a very interesting problem. Again, I'd be happy to talk with anyone who's interested. I'll end there, and thanks for your attention.